In this video, I'll discuss about atmospheric stability. What is stable atmosphere? Consider a parcel of air at some given altitude and it has the same temperature and pressure as the air surrounding it. If the air parcel is lifted slightly, it will experience less atmospheric pressure. If you see the picture, with increase in altitude, atmospheric pressure decreases. So, if the air parcel is lifted slightly, it will experience less atmospheric pressure, causing it to expand. This expansion requires energy, which comes from the parcel's internal energy. As a result, temperature of the air parcel drops. So at the higher elevation, the parcel is now colder and denser than its surrounding air. As a result, the parcel will want to sink back down. That is, whatever it was that caused the parcel to start to move upward will immediately be opposed by conditions that make the parcel want to go back down again. This atmosphere is called stable atmosphere. Now, what is unstable atmosphere? Suppose a parcel of air is lifted slightly. If its temperature remains greater than that of the surrounding air, if its temperature remains greater than that of the surrounding air, it will be less dense than the surrounding air and will experience buoyancy force that will encourage it to keep rise further. This initial upward motion will be reinforced and the parcel will continue to climb. This atmosphere is called unstable atmosphere. Now we will know some important definition or important notes to remember. We know air temperature decreases with an increase in altitude in the atmosphere. You can see in particularly in troposphere, with increase in altitude, the air temperature decreases. So the rate at which air temperature decreases with an increase in altitude in the atmosphere, particularly in troposphere, it is called lapse rate. If a parcel of air expands and cools or compresses and warms with no interchange of heat with its surrounding, this is called adiabatic process. You can see here, with increase in altitude, if the air parcel expands and cools, or if you go down, it compresses or warms with no interchange of heat with its surrounding, then this is called adiabatic process. But as long as the air parcel is unsaturated, that the relative density is less than 100%, the rate of adiabatic cooling or warming remain constant, and this rate is 10 degrees centigrade per kilometer or 1 degree centigrade per 100 meter of change in elevation. So it is called dry adiabatic rate or dry adiabatic lapse rate. So as rising air cools, its relative humidity increases and the air temperature approaches the dew point temperature. When the air cools to its dew point temperature, it becomes saturated and the relative humidity reaches 100%. Further lifting results in condensation and latent heat is released inside the rising air parcel. So this latent heat warms the air parcel. So the heat partially counteracts this cooling effect and and hence the air is no longer cools at the dry adiabatic rate, but a lesser rate is called moist adiabatic rate. Unlike the dry adiabatic rate, the moist adiabatic rate is not constant but varies around 4 to 7 degrees centigrade per kilometer. However, a reasonable average value of the moist adiabatic lapse rate in the troposphere is about 6 degrees centigrade per kilometer. Now, the ambient lapse rate or environmental lapse rate is the actual rate of temperature decreases with height in the atmosphere. It depends on number of factors such as wind speed, sunlight, and geographical features. That's why the actual ambient lapse rate or environmental lapse rate in the real atmosphere differs from the dry adiabatic lapse rate. So difference between the ambient lapse rate and the adiabatic lapse rate determines the stability of the atmosphere. Now we discuss about the superadiabatic lapse rate. When the environmental lapse rate exceeds the dry adiabatic lapse rate, that is environmental lapse rate is greater than the dry adiabatic lapse rate, then the lapse rate is called superadiabatic. So in superadiabatic condition, the ambient temperature profile for air cools more rapidly with altitude than the dry adiabatic lapse rate, and the atmosphere at this condition is absolutely unstable, and the air will always want to move to some new altitude. In this figure, if you see line A for this superadiabatic lapse rate. Now when the ambient temperature cools less rapidly with altitude than the moist adiabatic lapse rate, that is environmental lapse rate is smaller than moist adiabatic lapse rate, it is called subadiabatic lapse rate. The atmosphere is in this condition is absolutely stable and the air wants to stay where it was. In this figure, it is line B. And the region between these two lines may be stable or may be unstable. It depends on the actual ambient temperature profile and the actual adiabatic profile. The region is called conditionally stable. Now we discuss about atmospheric stability in a dry atmosphere. Dry atmosphere, that means here dry adiabatic lapse rate will be taken into account. So case 1, imagine an ambient temperature profile is superadiabatic, that is environmental lapse rate is greater than dry adiabatic lapse rate. Suppose a 20 degrees centigrade air parcel at 1 kilometer to be just like the air surrounding it. If the parcel is raised to 2 kilometer, it will cool adiabatically to 10 degrees centigrade. So at the first position, the air parcel was at 1 kilometer height, 1 kilometer altitude, and its temperature was 20 degree. And if it is lifted to 1 kilometer more, then in the new position, its temperature is 10 degrees centigrade at this 2 kilometer altitude position. But in this position, what is will be the ambient temperature? You can see that the ambient temperature at this point is 0 degree centigrade. So the 10 degree centigrade air parcel at 2 kilometer is now warmer than the surrounding air. So it is less dense, more buoyant, and want to keep rise. So in other words, shoving the parcel of air up in a superadiabatic atmosphere create force that want to keep it moving upward. Conversely, a parcel of air at 1 kilometer that is nudged downward become colder than the surrounding air, and so it keeps sinking. So if from the first position, if I nudged this air person downward to 0.5 kilometer, so its temperature may be at 25 degrees centigrade here, but the ambient temperature will be is 28 or 29, something like that. So it is, the air parcel is colder than the surrounding, so it keeps sinking. So it doesn't matter whether the parcel of air is nudged up or down. In either case, it keeps on going and the atmosphere is said to be unstable. Case 2, suppose an ambient temperature profile is subadiabatic, that is ambient lapse state is less than dry adiabatic lapse state, and we consider the same thing here, and the air parcel is nudged upward to 2 kilometer from this position, so it cools adiabatically from 20 degrees centigrade to 10 degrees centigrade. But as the atmosphere is subadiabatic, so the outer environment or surrounding environment temperature would be the 16, that is warmer than the parcel. So the 10 degree air parcel at 2 kilometer is now find itself colder than the surrounding. So at this new elevation, it experiences same pressure as the air surrounding it, but as it is colder, so it will be denser and sink back down here. Conversely, when a parcel starting from 1 kilometer and 20 degrees starts moving downward, if it moves downward, its temperature is 25 degree, but the surrounding temperature is less, maybe 22 or 23 degrees centigrade. So start moving and will get warmer, it gets warmer than the surroundings, so it becomes less dense than the surroundings, so the buoyancy force will push it back to this first position again. So in other words, anything that starts a parcel of air moving up or down will cause the parcel to experience forces that will want it to return to its original altitude. So the subadiabatic atmospheric profile is therefore stable. And what is neutrally stable atmosphere? For unsaturated or dry atmospheric condition, when the environmental lapse rate equals the dry adiabatic lapse rate, neutral stability occur, and in saturated air, environmental lapse rate equals to the moist adiabatic rate or moist adiabatic lapse rate. So in this case, under these circumstances, a displaced air parcel remains at its new position without accelerating upward or returning to its original level. So moving the parcel upward or downward result in its temperature changing by the same amount as its surrounding. So in this new position, it experiences no forces that either make it continue to motion or make it want to return to the original elevation. The parcel likes where it was and it likes new position too. And such an atmosphere is said to be neutrally stable. So you can read these references. Thank you. Thank you for watching this video.